what I'll be doing today is talk to you about some aspects of the work that I'm doing in a larger scopes, and hopefully you can also stop me in between if something is not clear. If you have some questions, you can also stop me, and hopefully we'll have some kind of a discussion as we go. So I have a set of slides, but these are basically to guide the discussion. So yeah, I mean, if you find anything uncomfortable not following, you can of course stop in the middle. So this is as Sadish said, this is a two-part series. So this is the first part of Particle Zoo. So this would be basically, I think most of it would be me talking and then you stopping me sometime in between asking me questions, but it'd be mostly me talking. So the second part of this would be, I think, next Friday, and this would be more like hands-on, like you also get to do some stuff rather than me speaking. So I'll be posing some small short exercises. I mean, it's not like homework. We do this as we go, and hopefully you'll get some sense of the excitement that this field has to offer. So that's the whole idea. Okay, so let's go um, uh, to this set of slides. So before we get into this particle, so this, what does particle zoo mean? All these things will be addressed in this talk. But before we get into this, let's talk about some fundamental questions. So there are these questions that I'm sure some of you would have thought of, like this is so innate in human beings, this curiosity about origin. So where do we come from? What are we made of? Where are we headed? So what is the future of this world that we're living in? So this is so innate to human beings. And so I actually want to show describe a little bit about this image in the background. This is the actually an image of the Milky Way galaxy, the galaxy that we are, our solar system is host to. And so this, you should take some time and maybe go to some of the very dark places in some place around you, and you can look up to the sky, and if the conditions are right, you would see this structure. This is the Milky Way. We are in the Milky Way, so we are actually looking into the Milky Way, this large collection of, this bright region of this object. This is the center of the Milky Way, so there are a lot of stars up there. And this is by far the largest structure that you can see using your naked eyes. There's nothing larger that you can see with your naked eyes from Earth. So, I mean, I would say it's a very spiritual experience to see this, because from one end of this, right from here to over here, the diameter is something like 100,000 light years. And we still don't have much clue what is at the center of this galaxy. I mean, although this year's Nobel Prize in Physics was awarded to an indirect detection of a supermassive black hole at the center of our galaxy. So yeah, so that's a little bit of background of why I flashed these galaxy images here. So we started off by asking this curiosity question. So why do human beings have this innate curiosity? Oops. Okay, so what makes us curious? So let me try to answer this differently. So we can also ask this question. It has been observed that some kind of dolphin species, these dolphin species rescue, in some situations, human beings which are drowning at sea. And you might as well think that dolphins are nice creatures, but there is an expense involved in rescuing a human being. Why would dolphins do this? And the answer is a bit, it's quite intriguing. So the thing is that dolphins breathe using a blowhole right here at their snout. So they have to come up above the water to actually breathe. And this immediately brings the question, how do dolphins sleep? So what happens? How does the dolphin breathe when it's sleeping? So the way dolphins do is that dolphins, in some dolphins, the way they sleep is they do a partial sleep. Only one half of the brain sleeps at a time, and the other half keeps them active so that they can come to the surface of the water and use their blowhole to continue their breathing process. Now, this goes quite efficiently, but sometimes some dolphins might sleep both with both their brains, and then it might drown. And dolphins, as a social animal, they would rescue their fellow dolphins, and so this kind of behavior evolved out of the very fact that they have to come up to this surface to take the air. The same kind of circuitry is what is driving them to save human beings, in some cases at least, while they are drowning. Now, why do I say this biology in a physics discussion? So the reason is that I want to appreciate the fact that the human curiosity about understanding how the world works, this is largely in part shaped by biological evolution. So millions of years of evolution has shaped our brain to be curious about things around the world. So this has helped us to survive African savannas. It has helped us to be vigilant and cautious out there in extreme harsh conditions in the forest. So that kind of biological wiring is kind of triggering this curiosity to understand the nature. And so human beings, we have a history of roughly 500,000 years of evolution. And earlier societies of human beings, we lived as hunter-gatherer societies, and we were able to pass on new things that we learned. So for illustration purposes, hypothetically, this is a physics class somewhere in 200,000 BC. So what's happening here is that someone figured out how to make fire out of two stones, striking two stones. And they were able to pass this information to their generations. And this is the success of human species and human civilization, that they learn something and they pass it on to the subsequent generations to come. So we're all standing on the shoulders of the giants, which passed through the surface of the earth, learning from the experience and getting this knowledge passed on to us, and we also pass on this information and knowledge to the subsequent generations. It's quite like what we are doing right now. So once human beings stopped living in hunter-gatherer societies, this was after the last glacial maximum. So, the Earth had several cycles of ice ages and non-ice ages. So after the last glacial maximum, human beings started agriculture. This was one of the major revolutions. And we started living in societies, civilizations flourished, ideas came, human beings started living together, so that you need to have certain kind of systems, social structures. Art flourished. Knowledge has to be done to be generated and also passed down in a systematic way. So this was done within the context of civilization. So the early ideas about the origins of the universe. So I pick some random civilizations here. So what I want to highlight is the ancient Babylonian civilizations, the Greek, Indian civilizations and stuff. So the ancient Babylonians, Babylonia is a place around modern day Iraq, I believe. So they had this idea that Earth is a flat disk. Okay. and it has 3 layers of atmosphere and 3 layers of grounds. So, and this whole thing is immersed in a liquid, in a water system. That's what the idea about this universe, about the universe was. And in ancient Greek and also in ancient India, the idea was, it's a bit similar. There is in ancient Greek idea, there is this flat earth which is held by fishes, and these fishes are floating on the surface of the cosmic sea. And in India, there was this idea that there was this cosmic turtle or cosmic tortoise, I don't know what it is, and 8 elephants on top of this cosmic turtle is holding the earth, and that's a whole idea about um, the cosmic the cosmos from I think Amarakosa. And then further down the lane, Greek philosophers also, there was an intense intellectual tradition both in Greece and India as well. And there were ideas about, there were further refined and more realistic ideas about the structure of the universe. So there's this geocentric model of the universe where people thought that Earth is the center of the universe, and all the planets like Mercury, Venus, Earth, Mars, etc., and even the sun goes around the Earth. And then further down the lane, there was also this Copernican idea, which treated the sun as the center of the universe and all other planets revolving around the sun. And yeah, this is just an artistic image rendering the curiosity of human beings to look out into the universe and trying to understand what the universe looks like. So this is a spirit of, this actually shows the spirit of inquiry which human beings had starting the Renaissance age in Europe, roughly about 1400s and onwards. So then we can ask, these were all some early ideas about the structure of universe. And we can ask today, how do we answer these big questions? So today we use science to answer these questions. Does someone ask a question? Okay, no. Okay, so science is a product of this Renaissance spirit, which started in Europe. So this is a modern way of answering big questions like the origin of the universe and structure of the universe and stuff like that. So what we do in science, I mean, we all know what we do in science, but just to recap what we do in science. So we build and organize knowledge. So these knowledge, this is a very specific kind of knowledge. There are many, I mean, there are philosophers discussing about what are the ways of knowing and what are the kinds of knowledge. But in science, what we consider knowledge is something which is testable, without, I mean, something that is testable and explainable, and something which can also, body of knowledge can also give predictions about things that might happen in the future. So this kind of knowledge is different from other kinds of knowing, but let's restrict to the scientific way of knowledge for this scope of this talk. Now, I want to emphasize one thing. So here, when I say knowledge, it's not about collecting a lot of information. So to illustrate this, let me give you an experience, I mean, share my experience. So when my niece was very small, so she was 5 or 6 years old, I played this riddle with my niece. So I told her, okay, so you can pick a number, you can pick the largest number you can count, and I can tell you, I can always beat you by telling a number which is larger than that. Now, at that age, she was counting, she was beginning to count, she could count until 100. So she was not really sure what is past 100. But I could always say, oh, so if you say 100, I could say, oh, 100 plus 1. So that's a bigger number than what she says, right? So you see what I'm doing here. So I'm not really collecting some ideas, and I'm collecting some information, and I'm not, you know, blurping out this information up onto her. So I'm using some kind of systematic way of organized structure of knowledge and applying that and generating new information out of that knowledge that I know of. So science is like this. So you have a set of information, you make some model out of the set of informations, just like how I could add an extra number to the largest number my niece could think of. Uh, so you could come up with a system, a mathematically consistent system or something, in order to generate new information out of already known set of informations. So where do we stand in the universe of the hierarchy of sciences? So there's this on this scale, there is this length, unit of length. So perhaps you're not so comfortable or know about this notation, 10 to the power of 6, 10 to the power of 9. So all it means is that these are all large numbers as you go higher up. So 10 to the power of 6 means 1 and 6 zeros. That's a large number. That's 10 lakh. And then 10 to the 9 means 1 and 9 zeros. That's 1 billion. And likewise, it goes on. So you can also go down. So you can say 10 to the minus 6 is 1 divided by 10 to the power of 6. That's 10 to the power of minus 6. So this scale is called micro. This scale 10 to the 6 is called mega, and 10 to the minus 6 is called micro. So all these length scales have different names attached to them. So you will come to know about this, more about this in future. But the idea here is that so at the length scales of human beings, so human beings are typically order of 1 meter or at best 2 meters. So the kind of science that deals with objects at this level regarding human beings, the most, I would say the most challenging and advanced would be neuroscience, understanding the structure of human brain and the evolved features of human brain and stuff. And then also how human beings organize themselves. So how societies of human beings interact and what are their dynamics and stuff like that. So these things are handled by social sciences and stuff like that. And beyond that, let's talk about the length scale involved in the size of the Earth. Yeah, at this level, what becomes more important is the physics, astronomy, and also the motion of Earth around the sun and stuff like that. And also about the inner structure of the Earth, like what goes inside, the weather patterns. Then we can also go all the way up. We can talk about the structures of Milky Way. I mean, I in the introductory slides, I showed you the picture of Milky Way. And these things involve, I mean, cosmology is the branch of science which involves dealing with these kind of structures in the universe. So what we would be doing, or my area of expertise, is something lower than this, like lower than the micro scale of lengths. So we'll be focusing in this region of length scales. So science is a vast body. It's a growing body of knowledge and information structures. And we'll be talking about subatomic structure of, science dealing with subatomic structure today. So we had asked about the structure of universe, but now we can also ask about what are the building blocks of the universe. So there were early ideas about what is the universe made of. So even in early Indian and Greek and to some extent Chinese and some of the Eastern knowledge tradition, there was this idea that the entire universe is made of 4 or 5 elements. Depending upon cultures, this number changes from 4 to 5 and things. So basically the idea is that earth, water, fire, sky, these are the uh, classic basic elements. So you only need these elements to make anything around. This was the early ideas. So this was, you might find this a bit childish or silly, but at that point of time, without knowing too much about the details of the nature of the materials around, people were really thinking in terms of the macroscopic things that they could see through this or through the senses, touch through the senses and stuff like that. So basically they decided, oh, there are 4 or 5 properties which is the only necessary to make all the things that we see around the world. Now today, that's not true, and the early hints of uh, the falsehood of this whole classical element theory was kind of apparent during the early days of chemistry. And I would pick a time point and say that it was John Dalton's atomic theory, which was proposed in 1800s. This was the first hint of the death of the classical element theory. So basically what John Dalton did is that he made a set of observations. So at that point of time, he was doing measurements with gases like oxides of carbon. So there are 2 oxides of carbon, carbon monoxide and carbon dioxide. So he made the specific observation that 100 grams of carbon reacts with 133 grams of oxygen. That's one way of making the oxide of carbon. Then 100 grams of carbon can react with double, like 133 times 2, which is 266 grams of oxygen. So that's the second way of making another oxide of carbon. So the first one here is carbon monoxide, and the second one would be carbon dioxide. So he could say, oh, okay, atoms combine. I mean, he didn't know the idea of atom was not there. He could say that the simple ratios, like 2:1 is the ratio in which oxygen can potentially combine with carbon and produce gases like carbon monoxide and carbon dioxide. So this was the first hint that if this can only happen if there are only finite elements combining to form compounds like complex gases. I mean, carbon dioxide is not a complex gas, but gases like that. And then he also made observation about the absorption of gases by water. So certain gases dissolve very easily with water. So he observed that carbon dioxide actually dissolves much better. This is the sparkling water or soda, much better with water than, for example, nitrogen. So he guessed that this might have something to do with the weight of this fundamental constituents of these gas. So this idea of atoms evolved from these kind of observations. So then it became clear that there are more to it than the classical element idea. Like there are more constituents which can combine in simple ratios and which are the basic constituents of matter that we see around. So then in 1871, I mean, chemistry was evolving quite fast. So once you have identified several of these elements, then what you would try to do is that you would want to try to make some sense out of this. So, I mean, science is not just stamp collection, right? So you want to put things together and see if you can reduce this whole information into something which you can make sense out of. So in 1871, around 1871, Dmitry Mendeleev, a Russian chemist, proposed this periodic table. This was quite remarkable. He could organize these elements by their atomic weight, and he could also, if you look at these tables, you would see certain gaps in these. So these gaps correspond to elements which were not known at the time Mendeleev published this periodic table. But the brilliance of this whole endeavor was that Mendeleev could say that, oh, there must be something here which we don't know, but there has to be something here. And later years, it was confirmed. There were several new elements discovered based on this um, Mendeleev's ideas of organizing elements in this particular structure. So that gave some idea about how. So later, so you can see here, there are several groups, there are several rows in these, and there is a reason why these rows exist in this kind of classification scheme. So this is actually, if you really think about, this is actually the first hint of structure of a finite structure for atom, like a substructure for the atom, like electrons or the nuclei. So then in 1900, Rutherford did a set of experiments. So by early 1900s, radioactivity was discovered. So it was observed that certain particles spontaneously emit certain charged particles, like alpha rays and stuff like that. So this was quite fascinating at that point of time. People even had watch dials painted in radium. So you could see fluorescent light coming out of their watch dial. So unfortunately, a lot of people who worked in those watch industries died because they were exposed to radiation, which at that point of time they didn't know was harmful to health. So this was quite fascinating at that point of time. Like, there's this substance, you keep it somewhere, and then you bring a photographic plate nearby, then something happens to the photographic plate, or you bring a scintillation plate, then you suddenly see light coming up from this particular scintillation plate when you bring this into this source of radioactivity. So everyone played with it, businesses played with it, even scientists played with it to understand things deeper. So what Rutherford did was that he put this alpha particle source, alpha rays is a radioactive ray, and then he made a small orifice to the source. This was covered in a lead block so that you don't get particles running in all directions. So you only get particles going in this one direction. And he put a gold foil, which is a heavy, gold is a bit heavy. I mean, compared to carbon or oxygen, gold is a heavy atom. And then, then he also put some fluorescent screen around this gold foil and tried to do some experiments. So what he found is that most of these alpha particles, they pass through this gold foil and then hit the fluorescent screen behind, and you see the light there. So the most intense fluorescent light is seen here. But there are also some deflections in some small angles. But what's also striking is that he saw alpha particles reflected directly back in the direction of the radiation of alpha particles. This would mean that there must be something really massive in this gold foil. So this observation made Rutherford to propose a model for the atoms. So he said, "Oh, okay, so there must be a very massive center in the nucleus, and all the electrons might be going around this massive center. The massive center would be a positive charge in order to cancel all the negative charges going around." You could also argue that why can't all these negative particles go inside and sit with the positive particles? There are some reasons that this wouldn't happen. By 1930s, with the advent of new mechanics, which is called quantum mechanics, it was clear that kind of a scenario would not exist. But let's not discuss that today. Um, so then, after the discovery of the proton, people actually thought that, yeah, just as the Rutherford atom. I mean, this is the Rutherford atom. Rutherford thought, oh, there's electrons and protons, and that's all to the atom. But then again, people were doing games with radioactive sources, and somebody discovered that, oh, there is another particle which is neutral, uh, which is not a gamma particle, much heavier than the gamma particle. So they said, okay, this must be a heavy neutral particle which must exist in the atomic nucleus. And this was discovered by 1930, and I think in 1936 or 35, James Chadwick got Nobel Prize for the discovery of neutrons. So typically what would happen in radioactive nuclei is that a neutron would become proton. Now, neutron is a neutral particle, and proton is a positive charge particle. So in order to balance the charges, when a neutron emits a positive particle, it should also emit a negative particle. And there's another Greek letter here, nu E, with a hat on top. This we can talk about this later. You don't have to know about this right now. So by 1930s, it was clear the atom model has to be revised in order to have an electrons going around this atomic nuclei, and the nucleus itself consisting of both protons and neutrons. And early 1911s, it was clear that there are some mysterious particles coming from outer space and hitting the Earth's atmosphere. So how did people detect this? So Victor Hess was doing some balloon experiments, like uh, sending some instruments up into the atmosphere, and these instruments would detect some particles which nobody has any clue where they come from. And then it was postulated, and later it was understood that these particles are coming from outer space. So they are constantly bombarding um, uh, the upper layers of Earth's atmosphere. And you see, they come. These particles coming from the outer space, and while they enter Earth's atmosphere, the Earth atmosphere contains atoms like nitrogen and oxygen. And what happens here is that they hit with these atoms or atomic nuclei of these nitrogen and oxygen, and then they produce certain other particles. So you can see a huge number of particles which are coming from these cosmic ray interactions. So then this was something new. So people started studying details about this. They started sending more balloons up into the atmosphere and try to study what's happening in these cosmic interactions in the upper atmosphere. Then soon it became clear that there's a huge list of particles that are produced in the upper atmosphere. So there are neutrons produced, and you can see there is certain Greek letters, pi, mu. So likewise, this huge list of particles which people were able to discuss by studying this cosmic rays. Now, one thing which became very clear to people who were doing this cosmic ray particles was the original particle which is entering this atmosphere, Earth's atmosphere. This is very high energy particle. Now, you can send your balloons up in the sky, and cosmic rays, they do have a frequency of coming to the Earth. But if you want to collect more particles, you should be able to somehow create this in your lab in a controlled way. Like you must be able to design an experiment which produce, for example, let's say these pi particle in abundance if you want to study details of this structure of this pi particle. So how do you do this? Uh, so this was the early 1950s, and beyond that, people had this idea of doing this controlled generation of particles in the laboratory using device called accelerators. So the idea is very simple. So you start with, let's say, a proton from here, and then you accelerate this by introducing positive and negative charge as alternating positive and negative charge. So if, let's say, this is negative at the instant when this proton is emitted from this S source, so this is a positive particle, this gets attracted here. And once it gets attracted and reaches the center of this, let's say, cylinder, the polarity changes. So this negative becomes positive, and the next cylinder's charge changes to negative. So now this positive particle at the center of the cylinder experiences a repulsive force because this negative charge became positive. It experiences a repulsion. At the same time, it experiences an attraction from the next cylinder. So you do this in several stages, and if you do this multiple times, so there are several cells here, cylinders here, C1, C2, C3, C4, then you can increase the energy of this original proton. So you start with some low energy proton here, and then you come out with a very high energy proton. And now you can bombard this on a target, let's say a lead block or something. And out of this interaction, you can produce particles just like how you can produce particles in cosmic rays. Now, the only difference is that you can do this, you can send many, many protons through at a given time, and you can increase the rate of production of the particles that you want to study. Maybe you want to study pions, so you send these protons at a very particular energy, and then once they're bombarded with lead block or something, you get a lot of pions, which you can study in your lab in a controlled way. So this is the whole idea of accelerator physics. So you can start with a particle, then you subsequently increase the energy of this particle in several stages, and then bring them to collisions on a fixed target. Or maybe you can put another accelerator on the other side, and then somehow align these paths of both protons coming out of this cell, and then they would hit head on. And then these kind of accelerators are called colliders, because they are colliding two particle kinds. Now, accelerator physicists started building more sophisticated accelerators, increasing the energies, and they collected a huge list of particles. So once you have such a huge list of particles, what would you do? I mean, you need to make some sense out of this. So here, this is a very funny looking image, right? So this is some kind of structure where you have a lot of funny characters on the vertices of this object. So you see, we ran out of all these Greek alphabets, and then we started using English alphabets and stuff here and there. So the way this is organized like this, like a 3D structure, comes from this organization comes from a person called Murray Gell-Mann. Gell-Mann essentially created a table, a periodic table, like how Dimitri Mendeleev created a periodic table of atoms. Gell-Mann created a periodic table of these particles which are discovered in the accelerator and cosmic ray experiments. I mean, the only thing is that Gell-Mann's periodic table looks a bit funny compared to Dimitri Mendeleev's periodic table. And then, as I said, when Mendeleev organized atoms in the periodic table, it was kind of getting clear that there is more structure to the atoms. There's electrons, and there is a very specific scheme of filling the valence shell of the atoms, and that's why you would see certain structures in the periodic table. Just like that, Gelman also made some observation, and he said, "Oh, there must be something more fundamental why I can arrange these particles like this." And this was the birth of the quark model. So Gelman said, "Oh, okay, so this huge list of huge zoo of particles, can we make some sense out of this?" Gelman said, "Yes, we can." He said, all these particles, protons, neutrons, pions, like this pi particle here, then this eta particle here, then there's this rho, all these particles are made of smaller sub-constituents. These are called quarks. So then this model was quite successful in explaining this multitude set of particles which were observed in the accelerator experiments. And parallelly, there was also another periodic table evolving. So Gelman said these are the set of quarks. So there's this up, down, charm, strange, top, bottom. These are the quarks, which are constituents of these new particles that are discovered in accelerator experiments. Then there are also the other fundamental particles, these electrons, which need to be part of this whole grand scheme of list of particles that we know of. Then you must have also seen from previous images the mu particle, which is quite similar, has quite similar properties as electron. Only difference is that it's a bit heavy than electron. And then there's this tau particle, which is also quite similar in properties of electron, but again, it's the most massive of this whole list here, bottom down here. And these are the quarks that Gelman proposed, and some of the quarks which Gelman proposed were not discovered at that point of time, and very late, as early, I think as late as 1990s, the top quark was discovered in the 1990s. So this was not, this was proposed by Gelman, and at that point of time when he was proposing this, nobody had any clue there would be top quarks. The elements that we know of, that the world that we live in, these are made of this set of particles. Like the protons are made by two up quarks and down quark. Then of course there's this electrons, and then yeah. So the other particles, this charm, strange, top, bottom, all these things are unstable, and they would decay into this set of particles, which are called first generation particles. So the standard model says there are three generations of particles. So this is the first generation, this is the second generation, this is the third generation. So just like Mendeleev's periodic table, but a little bit more simpler than that periodic table. Then the standard model also says that there are other particles. So you can see some particles named here with the G. This is gamma, then Z, W. So these are particles which are responsible for the known interactions in the universe. So we know that electrically charged particles interact with each other, and these interaction is caused by this gamma particle or the photon. So when electrical charged particles interact with each other, they exchange this photon, and that's why there is this electrical interaction. And then, the protons are held inside the nucleus. I mean, protons are in positive charge. They would repel, but still, how does the proton club together, and how do they get held inside this nucleus? So this is because there is another force responsible for holding these protons. These are called strong force, and the strong force is mediated by this particle called the gluon. And then there are other particles, W and C. So these particles are actually responsible for the radioactivity. Now there is something which is missing here, gravity. I mean, gravity is one force we all experience. I mean, we see things falling. Yeah, I mean, we know we are going around the sun, the Earth is going around. So all this is mediated by a force of gravity. Yet, in this description of particles, the standard model of particle physics, we don't know why gravity cannot be fit in. There are some theoretical problems on how to fit gravity in this. So maybe this is a problem for one of you to solve in future. So yeah, there are open challenges for you guys. And then on this corner, there is this particle called the Higgs boson. So this particle was proposed in the 1960s. So one thing I didn't tell you is that all these particles have different masses. So here you can see the mass is written as 2.3 MeV per c square. I mean, don't worry about this. Let's call this unit. So this is 2.3 units. And this is actually GeV per c square, which is giga, so which is actually 1,000 times the MeV. So this would be actually 1,275 units when we compare. So this charm quark is 1,275 more heavy, more massive, sorry, heavy is wrong, but massive than the up quark. And likewise, so all of them have different masses. And nobody know why exactly these things have different masses. And it was proposed in the 1960s that this is because all these particles interact with another particle called the Higgs particle in a different way. So if the up quark, so this is a light quark, so this doesn't interact to the Higgs particle as strong as the charm quark. So that sounds fine. Okay, that's a nice idea, but ideas are important in science, but you also should have some experimental backing for the ideas. Okay, somebody proposed this is what's happening, but I mean, are we sure this is what is happening? So people was looking for the Higgs boson for several years, like 50 years, and this was not found. This is the person, Peter Higgs, who, I mean, he's writing down the equation here through which he explains, I mean, this equation, what he writes here is explaining why or how the fundamental particles like electrons, up quark, down quark, etc., attain masses and different masses for that matter. And in 2012, I'm just flashing this complicated looking plot here, but this is a plot which was shown in 2012 from an experiment which I'm working on. I'm working in the Atlas experiment, and this is from CMS experiment, which is another experiment which is working in the Large Hadron Collider. So this Higgs particle was discovered in 2012, making the standard model complete. So all particles which are predicted by the standard model has been observed. But of course, that's not the full story. The standard model doesn't describe the whole universe. We'll come to that later. Oops. Okay, so this was a huge thing. A lot of newspapers wrote a lot of things about this across the world, across, multiple languages. Everybody celebrated the discovery of Higgs particle in 2012. And this is a picture of Peter Higgs, who's the person who proposed originally this particle in 1960, and this is the Director General of CERN, the organization which runs this experiment. So now, yeah, so what is the picture that we have of this universe now? So at several scales, you can explain this at several scales. So at the cellular level, in microscopic regime, so you have the chemistry and the biochemistry describing the dynamics and mechanisms of things. So how cells organize themselves, how cells communicate through the membranes and stuff like that. And if you go one layer down that, you will reach the molecular level, or molecular biology. So you can talk about the structure of proteins and how proteins get built from the DNAs and stuff like that. And if you go again one step down, you reach the atomic scale, where you have massive nucleus and electrons going around this massive nucleus. And if you go one step further down, into the nucleus, you would see that the particles in the nucleus, the protons and neutrons, they even have can be again divided into finer substructures, uh, which are made up of these quarks. Now, you could ask this question: can electrons be broken down into smaller particles? Um, the answer is we have looked for that, but we haven't seen. But it's an open question. We haven't seen finer substructure for electrons, but for the neutrons and protons, yes, there are. Now you can also ask this question if the quarks can be broken down into finer particles. Again, it's open. We don't know if this can be done. Maybe it's something for you to figure it out. And then we have this grand scheme or grand model, the standard model of particle physics, which explains all the known particles here. I mean, if you really think about it, you only need this up and down quark to produce neutrons and protons, and that's all is making up the atoms, the molecules, and the cellular structure, you, me, the things that we see around. And then standard model is not just a table, it also has a mathematical structure for it, and there is a complicated looking equation which describes the structure of the standard model, which you can learn about these things yeah, later. I mean, let's not complicate things at this point of time. So then of course at the center of this there's Higgs particle, which is responsible for giving mass to the fundamental particles like quarks and electrons and muons. And there's a technical term for this. The term is the Brout-Englert-Higgs mechanism. I mean, it sounds a bit complicated, but it's the name of the people who primarily worked on this. So yeah, Francois Englert, I forgot the first name of Broad, but Peter Higgs. So these are the people who worked on this. So that's the mechanism of generating mass for the fundamental particles is named in honor of these people. So this talk will not be complete without me describing the Large Hadron Collider. So I spoke a little bit about accelerators, how people came up with the idea of generating particles in laboratory by sending particles and accelerating them in a controlled way. And the largest of this, so since 1950s, we've been doing this. And the largest of this available today is the Large Hadron Collider in Geneva. So you can see here, there are several pipes going through. These are complicated structures. So there are two pipes going through. So actually what's happening is you can send proton beam through one of these pipes in this one direction, and then another proton beam in the opposite direction. And then you can bring these things into collisions by crossing these particle beams. So that's what happens here. So this is a 27-kilometer ring. So so the tubes that you see here, they go around this tunnel in 27 kilometers. So it's really huge. And there are several points here, like there are several experiments, these named in a funny way. Alice, CMS, LHCb, Atlas. So I work for Atlas experiment. So this is the other experiment, which is a very specific experiment for doing some specific things. So this is where my wife works at. And this is CMS experiment, which is exactly opposite to the Atlas experiment and in this ring. And Atlas and CMS, these are the large experiments which are going in this LHC. So these are general purpose experiments. They can do several measurements, and they've been producing results. They're the ones. They're the two experiments which found they discovered the Higgs particle. So yeah, so that's about it. And these things are pretty complicated. So you can see a lot of, so these are the snapshots of CMS here, Atlas here, Alice and LHCb. LHCb and Alice are a little bit smaller, but CMS and Atlas, these are huge experiments. These are like really like 10, 15 stories high. And you can see a lot of electronic components going in. So this is like a very complicated camera. So when you bring particles through these experiments and collide them, they produce secondary particles. The collisions produce particles, and these particles can be in some way clicked, or a snapshot can be taken using these complicated electronic machinery. Um, so once you do that, when you take these pictures, it looks something like this. This is again very simplified way of describing it. So there's several particles flying in and around, and that's what you see when you take these kind of pictures. And this is again a signature, like how this is a signature of Higgs production at the LHC. Uh, and we have many such events, and this is how we infer the production of Higgs, and also we study the properties of Higgs. Uh, so so we not just make photographs, we also make plots and graphs. So here you can see funny looking structures. So I mean, this is a bit complicated to explain, and I'm not going to bore you by explaining this, but just want to say that this thing that you see here, this tower-like thing, this is what the Higgs looks like in terms of, I mean, in a scientific way, this is how this is how a Higgs boson would look like. Okay, this is again a complicated plot. We don't want to discuss this now. So yeah, and then as I said, the standard model is complete. So all the particles in the standard model is described and it's discovered. But is that all? No, there are still things that we don't know. First of all, gravity is not part of the standard model's description. So there must be a way to make the description of gravity part of the standard model. And then there are these questions like, where do we come from and where are we going? So we have some kind of an idea how the universe originated. The universe originated in something like a big bang, where the space and the space-time started expanding rapidly, and then stars, well, not stars. First of all, quarks and gluons formed in the early age of the universe. Then the universe started cooling down, and these quarks start combining to form nuclei or particles like nuclei, and then hydrogen atoms start forming, and these hydrogen atoms starts organizing into stars, and these stars produce other heavier elements up until iron in their cores during the nuclear fusion process. And that's what we know about the history of the universe. And we are still trying to understand where are we headed, like what is the future of this expansion. So we know that the expansion of universe is caused by some mysterious energy. This is called the dark energy. No one has a clue what this is. The still ideas around, people are trying to test these ideas, but there's nothing clear about what exactly this dark energy is. So this is something really puzzling, and this is one of the burning problems in modern cosmology. What is causing this accelerated expansion of the universe. Then there's this question, why do we exist at all? Like the hydrogen atoms, they under the self attraction of gravity, they form stars, and then inside these stars, these elements forge up until iron. And why do these galaxies form? I mean, what is the reason behind formation of these stars and organizing into these galactic structures? So there's some ideas. We know there is another mysterious matter in the universe. This is called dark matter. And if the dark matter was absent, we wouldn't have formed stars in the galactic dust. So we have some hints about the existence of dark matter, like the observations from cosmology, which really tells that there is matter out there which interacts only gravitationally. We haven't known any other kind of interaction of this matter. So that's also quite puzzling at this moment. We have no idea what this is, but there are experiments looking out for this. Yeah, so what are we made of? We already kind of have some idea. This is the whole structure of things. We also describe this. We start with quarks, then formation of the protons and neutrons from these quarks, then atomic nuclei, then atoms, molecules, then biomembranes, as we know of, and larger structures like the Earth, the other planets, the solar system, galaxies, clusters, superclusters, and stuff like that. So, yeah. So then there is other intriguing questions, like there's some theoretical considerations in so people are trying to combine gravity with a sort of a standard model, like using a quantum description of gravity, quantum mechanical description of gravity. And there are some ideas coming out of this, like there are questions coming out of this, whether the universe that we live in consists only 3 space dimension and 1 time dimension, other dimensions. So these theories says there could be other dimensions, but we haven't seen this. So that's something we really need to find out. And yeah, so what is holding matter together? So I've told you earlier that without dark matter, we would not be able to see matter clustering and forming structures like these galaxies here. So that's something we also need to understand. So this is Vera Rubin, who discovered certain properties of the galactic motions, and it's from her observation that we have some idea. There must be something out there like dark matter. So if you put all these things together, the known matter in the universe, so the stars, planets, galaxies, that only make up until 0.5% of the known matter in the universe. And then there's other stuff in the universe. There's this interstellar gas. So universe, we would like to think it's an empty space, but there are hydrogen and helium gas which are in this space, in this interstellar space or intergalactic space. So that amounts only up to 4.5%. So this is the matter that we can see. The matter that we can see, when I say see, it means visually see. Also, we can detect experimentally using our instruments. This only makes up to 5% of the known matter. And the 27% of the matter, we don't know much about this 27% of matter. This is the dark matter. We know they interact gravitationally. We have seen evidence for them interacting gravitationally, but we know nothing else about them. And then there is this another 68%, which is responsible for the accelerated expansion of universe. And this, no one really has any clue um, what this is. So there are a lot of unknowns. I mean, even though the standard model of particle physics is complete, there are a lot of unknowns, and we would like more younger people to jump into this adventure and try to seek answers for these questions that we don't know. Now, so can we answer these questions, right? I mean, are we in a position to answer these questions? So this image that you see here in the screen, this is taken by the Voyager mission. So this is actually showing that highlighted blue dot that you see in the screen. This is the image of the Earth. So even in the length scale of the solar system, the Earth is so insignificant. But yet we human beings are able to come up with ingenious ideas, think about the origins of the universe and structures in the universe. And we have some fairly good understanding about what the universe is made of. There are open questions. There are more open questions than things that we know of. But we have proven we can understand things by continuing this pursuit, and there's no reason to think that we will not be able to find answers to these questions. So it's up to the generations to come to find answers to these questions and generate new questions to pass on to the subsequent generations to understand the structures of the universe. So yeah, now how can you be part of this story or part of this journey? So you can get involved in some of these experiments. So there's this program from CERN, which is called the Beamline for Schools, where basically you are supposed to submit an idea to the CERN research body. As a school, you can do it as a group of students, your friends, and then they will select some ideas and you will get some time to be at CERN and do some experiments. So that would give you some excitement and also a hands-on experience on how things are done at CERN and things like that. So hopefully such experience would help you in pursuing these kind of studies. So, and then the CERN summer school program, which you can apply independently. You don't have to submit a project proposal, but you can apply for a summer school program, which is a 2 month program which happens in Geneva during summer. I think you have to be in your undergraduate or something. Probably you can't apply when you are in your school, but once you move into the college, you can do this. And you get to work with researchers who are working at CERN on real problems. They will share some of their research problems with you, and you can get your hands dirty with that and see if you like what is being done in understanding, in pursuing this kind of studies. Yeah, so that's all from my side. So I'm sure there would be questions.
So I actually had one question. Like, where
Yeah.
does dark energy come from?
Oh, that's a good question. So we don't know this. So let me answer it differently. In case of dark matter, we have some hints what it is. Like we have seen there is a specific property of gravity which is called the gravitational lensing, which is a property by which gravity can bend the light ray. So we have seen dark matter bending lights around it. However, this is not the case with dark energy. We know the universe is expanding at an accelerated rate, and there must be something driving this accelerated expansion, and that's all we know about dark energy. And it's called dark energy not because we have some, I mean, so human beings have this tendency that we name something, and then once we have a name attached to it, we somehow have a sense of understanding what it is, even though that could be a false sense. uh, and dark energy is, I would say, it's a name given to something which we really have no clue about. It might be a new form of force, responsible for the accelerated expansion of the universe. I mean, there is nothing in physics which says that there are only known four fundamental forces of nature. There could be other forces as well. So there's nothing restricting the number of interactions and forces that the universe has. Now, it could be a new interaction, we don't know. It could also be something missing in our understanding of the theory. Like, there must be a missing piece that we did not add to this matrix of the matter budget I showed you, right? 67% of the dark energy, 27% dark matter, and stuff like that. So that maybe we are missing something in that. So it's more mysterious. So dark energy is more mysterious in that sense than dark matter. So I don't think I have answered your question, but I kind of probably motivated you to think about this a little bit by giving some information.
Yes, sir.
So then what is the difference between a black hole and a dark energy?
Oh, so black hole is a totally different thing. So black hole is it is an object which is predicted by the general theory of relativity, which is Einstein's version of gravity. So you, so it is an object which is capable of attracting gravitationally attracting things in towards it. Now, which when I say that, it means that we can locate it in the cosmos. We can say, oh, this particular location has a black hole, and we even have made images of black hole for the first time. I think last year, the Event Horizon Telescope actually clicked pictures of a black hole for the very first time. So we know these things exist. Now, dark energy is more elusive. I mean, we have no real sense of what it is. So it's just a name given to something unknown. We cannot really say, oh, that thing that we see there out there, this is dark energy. No. So we see the universe as a property. It is expanding at an accelerated pace, and we think there is a force responsible for that, or there's something responsible for that. We call it dark energy because we have no clue what it is. Does that make sense?
Thank you, sir.
Yeah, I'm happy you're asking questions, so I can still stay here if you have more questions.
So, like, if the universe is expanding, it also has to contract, right? So, even for the contraction, the dark energy is helping, right?
So there are several ideas. So what you're talking about is, if the universe expands, then it would contract. So there is one class of idea which is called the pulsating model of universe. So the idea is that universe would expand, and beyond some limit it stop expanding, and then it would contract, and this cycle continues over several years. But because the universe has very specific properties, which I mean, I really can't explain the details here because it's a bit complicated. So because the universe, they talk about the geometry of the universe. Because the universe has a specific geometry, it's now we know that it's not possible for universe to contract. It will continue to expand like this. And what's going to happen is um, the expansion will actually rip off atoms in a very specific way. I mean, there is in the atom, the electrons and the neutrons and the protons are packed in a way, and you can think of some kind of specific, interatomic or inter-electron distance scales, which is typically of the order of Armstrong, like 10 to the power of -10. That's the length scale involved. Now, if the universe continue to expand like this length will increase, and eventually everything would die out like that. So, with the, because the universe has this particular geometric property, it would not contract. That's our current understanding. It will continue to expand and die out, what we call as a heat death, because it is an expansion. If we continue to expand, the universe will cool down. So right from the Big Bang, from the Big Bang, the universe was a hot, dense medium, and it started cooling via this expansion. Now it will continue to expand, and it will lose its temperature, and it will undergo what they call as a heat death. So that's what's going to happen. But don't worry, this will, our solar system will be destroyed much before that. The sun would die much before that. So we have other things to worry about.
So, sir, then the universe is like a rubber band now. So if we keep expanding, one day it will break like totally.
Yeah, so there is this analogy of using a rubber sheet to explain the expansion of the universe. Now, the problem with analogies is that there is some place they break, like they don't really. The reason that you depend on analogy is because to simplify certain things. So the analogies break beyond a point. The analogies don't hold good. So you're right, when you start expanding a rubber sheet to, how much ever possible, beyond a point it would break. But the expansion of the universe is not like that. The universe expands by adding more rubber to the medium. So if that's an analogy, I can say it adds more rubber to this rubber sheet so that you can continue to do this pulling apart these rubber sheet in different directions, so it would not break. So the universe adds more space-time while it expands.
Okay, sir. Thank you.
Yeah, that's a good question. Yeah.
Sir, can I ask one question?
Sure.
Sir, can we reverse time? Suppose if there was a medium that we can reverse time, will it affect the universe?
Oh, so this is time travel that you're talking about, right?
Yes, sir.
Yeah, I only have fictional ideas of this. If the universe has extra dimensions, like we know there are only 3 and 4 dimensions. Three space dimensions and 1 time dimension. So if we find additional extra dimensions, then possibly we could do a time travel, but this is all at the level of fiction now. There's no clear indication that this is the case.